just confirm my audio video is clear to you. Audio video is clear. So a very good evening everyone. I hope you are doing good. I welcome you all to the YouTube platform of IMS GATE Academy. Myself Prateek Mishra, and we are conducting sessions on most expected concept for GATE-24. I am dealing with environmental engineering right now, and previously we have conducted sessions for very important topics of environmental engineering. Today we will going to have a session on design of sewers. My dear students, design of sewers and the question related to it are most frequently asked question in your GATE exam and also for other competitive exams. So if you are preparing for GATE in environmental engineering, design of sewers should be a domain or should be the area in which you should be more confident, right? So today we will going to see all the aspects, all the design parameters that are required for designing of sewers. So please give the heading design of sewers. Okay, first of all, what are these sewers? These sewers are pipes or conduits which are used to collect and transport the wastewater. And this wastewater is generated after different activities of the community, right? Giving you a short briefing about wastewater, my dear students, wastewater is basically of three types. First one is domestic wastewater, which is generated after domestic activity. Second one is your industrial wastewater, which is generated after industrial activity. Third one is your drainage, which is generated after rainfall event, right? In wastewater engineering, we precisely focus on sanitary sewage or the wastewater which is produced after domestic activities and industrial activities. So this wastewater which is produced in the community after different activities, the collection of this wastewater and transportation of this wastewater is made using pipes and conduits. These pipes and conduits are termed as sewers. So first of all, this wastewater is generated at your household, is collected using household sewers. So if this is your household, there are different pipes which are laid at your place, and these pipes are basically used to collect wastewater from your kitchen, from your washroom, from your basins. So all these pipes that are present at your house to collect wastewater from your house are known as household sewers. So these are known as household sewers. Obviously, these household sewers are present inside the home. Therefore, they are managed by the local resident. Means if I have my house, I have to manage these household sewers. I will not going to call municipal corporation if there any blockage in household sewer appears. So the maintenance of this household sewer is done by the owner of the property. Okay. From different houses, this wastewater is collected using laterals. So from household sewer, the wastewater is collected using laterals. The wastewater is collected using laterals like this, right? From the household sewer means all the pipes which are laid at your place, those are known as household sewers. From the household sewer, it is taken to laterals. Now laterals where you can see, just outside your house, these drainage that you see are termed as laterals. Different laterals take wastewater to branch sewer. So this is again one more lateral I have drawn. Different laterals collect wastewater and drop it into the branch sewer like this. Different laterals drop the wastewater into the branch sewer. This is my branch sewer like this. So like that you have different branch sewers. Different branch sewers will collect the water into mains. So this is my main sewer. And through this mains, wastewater is taken to sewage treatment plant, STP. This is sewage treatment plant. And from the sewage treatment plant, the treated wastewater is disposed into the source using outfall sievers. So from the sewage treatment plant, the wastewater is disposed into the source using outfall sievers. So how many types of sievers? First one is the household sewer. This is managed by the local residents. Then you have laterals, branches and mains. So L for laterals, B for branches or branch sewer, M for mains, main sewer. And then you have outfall sewer, OS. So these are the different types of sewers that are used to transport and collect wastewater. The lateral is the sewer of least dimension and outfall sewer is the sewer of largest dimension. You can just imagine or relate like this. There are different laterals from where water is taken into the one branch sewer. There are different laterals from where water is taken into one branch sewer. So obviously the size of the branch sewer should be more than the laterals. Then n number of branch sewers, n number of branch sewers like this take the water into main sewer. And main sewer takes this wastewater to sewage treatment plant from where this treated sewage is disposed of using outfall sewer. So if I talk about the size of the sewer, laterals are the sewer of least dimension and outfall sewer are the sewers of largest dimension. So talking about size of sewers, so laterals are of least dimension and your outfall sewer of largest dimension. Okay. Now coming back to this diagram again. All these sewers are connected using a unit which is known as manholes. All these sewers are connected using a unit which is known as manhole. This is manhole. All these sewers are connected using a unit which is termed as manholes like this. Like this, you have manholes present in your sewerage system. Now, if you look into the bigger picture of the sewerage system, your sewerage system comprises of sewers which are of 4 types. First one is laterals, branches, mains and outfall sewer. Second one is your manholes. These manholes are provided for maintenance work. If any clogging happens, then these manholes will be used to clear the clogging, right? So manholes are provided for maintenance work. Right. There are other locations also where these manholes are provided. We will going to see just now at what all locations these manholes are provided, right? So your entire sewerage system comprises of sewers and manholes. There are 4 different types of sewers: laterals, branches, then you have mains and outfall sewer, and then you have manholes. Right. Now where these manholes are provided. So next is location for or locations at which manholes are provided. locations at which manholes are provided. So locations at which your manholes are provided, right? I think I have written wrong spelling. These are manholes, not manholes. Manholes, right? So locations at which manholes are provided. The first location at which the manholes are provided is where size of the sewer changes. Where size of the sewer changes. So the locations where size of the sewer changes will provide a manhole. Where a smaller size sewer, this is a small size sewer, is meeting a large size sewer, there we provide a manhole like this. So this is my manhole, and on the other side of the manhole, this is the larger size sewer. Okay, so you can imagine lateral meeting a branch sewer or branch meeting a main sewer. Like that you can imagine. So wherever the size of the sewer changes, your manholes are provided. This is small size sewer and that is large size sewer. This is small size sewer and that is large size sewer. So wherever the size of the sewer changes, there we provide the manhole. This is the first location. Second location where we provide the manhole is where the alignment of the sewer changes. Where the alignment of the sewer changes. This is the second location where we provide the manhole. For example, so wherever the direction of the sewer will going to change, there we will provide a manhole. For example, if your sewer is going like this, right, and suddenly the direction of this sewer line you have to change, there you have to provide a manhole like this. This is the manhole that you need to provide. And after that only you can change the direction of the sewer like this. So wherever the direction of the sewer changes, there you need to provide a manhole. Sewer is moving along this direction, and here the direction of the sewer changes and now it's moving in this direction. So here you need to provide a manhole. So second location where you need to provide the manhole is where the direction of the sewer changes. Now the third location where you need to provide the manhole is where the slope of the sewer changes. Where slope of the sewer changes. So the next location at which you can provide the manhole is where the slope of the sewer changes. For example, if you are taking the cross section, for example, this is the direction in which sewer is laid, okay, and you take the longitudinal section. So this is how any sewer will look like, right? So here you can see there is some slope for the sewer. Say this slope is 1 by N1. There is some slope for the sewer, okay. Now if I have to change the slope of the sewer, what I have to do is, first of all, I need to provide a manhole like this. I have to provide a manhole like this, and after that only I can change the slope of the sewer like this. Now the slope is 1 by N2. So whenever the slope of the sewer will going to change, there you need to provide a manhole, okay. So this is how you provide a manhole where the slope of the sewer changes. The fourth location where you need to provide a manhole is where one type of sewer meets another type of sewer. meets another type of sewer. Where one type of sewer meets another type of sewer. Means if you have laterals laid like this, these are your laterals, okay? And if this lateral has to meet branch sewer, then before meeting, you need to provide a manhole at the junction. Laterals meeting with branches like this. You need to provide a manhole like this, right? Again, I'll give you one more example. For example, this is your branch sewer. And in this branch sewer, laterals are meeting like this. This is one lateral meeting. This is another lateral meeting. This is another lateral meeting like this. So, n number of laterals meeting the branch sewer. This is your lateral sewer. So, wherever this junction is there, lateral sewer meeting the branch sewer, here you need to provide a manhole like this. This kind of manhole you need to provide. So, wherever laterals are meeting branches or n number of branches are meeting your mains, there you need to provide these manholes. Okay, I have taken an example of laterals meeting branches. Same goes with when n number of branches fall out to main sewer. Okay, so these are the 4 different locations where you need to provide the manhole. The fifth and the most important location is on a particular type of sewer at some pre-specified distances. The fifth is on a particular type of sewer at pre-specified distances. At pre-specified distances, right? So you might have seen while traveling in any road, okay, you see these holes made. It is covered with these shields or top covers, right? These cast iron covers you see. So in a particular type of sewer, at some pre-specified distances, you need to provide these manholes for maintenance work. For example, if this is the main pipe or main sewer going like this. So this is the underground main sewer going like this, right? So in main sewer only, at pre-specified distances, you need to provide manholes like this. On a particular type of sewer, at pre-specified distances, you need to provide manholes like this. So these are the 5 different locations where you need to provide the manhole. First is where the size of the sewer changes. So whenever the size of the sewer changes, means smaller size sewer is connected to larger size sewer, there you need to provide a manhole. The second is whenever the alignment of the sewer changes, means if the direction of the sewer pipeline is changing, then it has to be done using the manhole. The third location is wherever the slope of the sewer changes, so that change in slope has to be made using this manhole. The fourth is whenever one type of sewer meets the another type of sewer, there you need to provide a manhole. This is the example, lateral meeting the branches. So every time you need to provide these manholes. Next one is in a particular type of sewer at some pre-specified distances, you need to provide these manholes. Okay. So why we are providing these manholes? These manholes are provided for the maintenance work. Okay. That is the only purpose for providing these manholes. Now, if I talk about the entire sewerage system, so sewerage system comprises of sewers and manholes. Why we are laying this sewerage system? In order to collect the wastewater and transport it to the sewage treatment plant, and then collecting the treated sewage effluent and disposing it to the source. These are the reasons why we are providing the sewerage system. Okay. Now, if I talk about the fluctuations in types of sewers, so you can give the next heading, fluctuations in sewers. So, we have 4 different types of sewers. First one is, okay, here I will write type of sewers and here I will write fluctuations. So, first type of sewer is your laterals. For lateral, fluctuation is 4. In just a small while, I will tell you how to use this fluctuation, okay. It is not a very complicated task. Next one is your branch sewer. For branch sewer, fluctuation is 3. For main sewer, fluctuation is 2. And for the outfall sewer, fluctuation is 1.5. As you can see, as the size of the sewer is increasing, the fluctuation in the wastewater is also decreasing. So, this is the common concept of statistics, whenever you increase the sample size, your standard deviation decreases, right. This fluctuation is nothing but how much the discharge is exceeding from the average value. That is what we mean by fluctuation, okay. So, now how to use this fluctuation? You observe this very carefully. So, for laterals, fluctuation is 4, for branches, fluctuation is 3, for mains, fluctuation is 2, and for outfall sewer, fluctuation is 1.5. Now, how to use this fluctuation? Observe this very carefully. So, for example, if I talk about laterals, for laterals, fluctuation is 4. Here I will give the heading laterals. How to use this fluctuation? For laterals, fluctuation is 4. It means that maximum hourly discharge, it means that maximum hourly discharge is equal to 4 times of average daily discharge. So, how we are using the fluctuation? Maximum hourly discharge for laterals is 4 times of average daily discharge. Next, minimum hourly discharge is equal to 1 by 4 times of average daily discharge. Is equal to 1 by 4 times of average daily discharge. So, this is how you should use, right. In raw water engineering, we were only worried about maximum daily demand, maximum hourly demand, like that. But in wastewater, we are worried about both the things, maximum hourly discharge and minimum hourly discharge. Okay. Why we are worried? Reason we will discuss in short while. First of all, you understand how we are using these fluctuations. For laterals, fluctuation is 4. It means that maximum hourly discharge is 4 times of average daily discharge. Second is minimum hourly discharge is 1 by 4 times of average daily discharge. Now, next one, if I talk about this branches, for branches your fluctuation is 3. So, again for branches I can write the same thing. So, for branches, or branch sewer, fluctuation is 3. It means that maximum hourly discharge in branch sewer. Maximum hourly discharge in branch sewer is equal to 3 times of average daily discharge. Is equal to 3 times of average daily discharge, right? Next one is minimum hourly discharge is 1 by 3 times of average daily discharge. Is 1 by 3 times of average daily discharge. So this is how you should use all the fluctuations. In the question, if you'll get, in the examination, if you'll get the question, it will be around branch sewer only, right? So maximum question, whatever are framed in the examination, they are framed considering branch sewer only. That's why if fluctuation will be given to you, it will be somewhere around 3, right? So you should focus more on this branch sewer. Like that, you can use fluctuation for main sewer, which is 2, and outfall sewer, which is 1.5. Again, I'll remind you, lateral sewer are the sewer with least dimension. Therefore, fluctuation in lateral sewer is the highest. Outfall sewer is the sewer of largest dimension. Therefore, the fluctuation in the outfall sewer is minimum, which is 1.5. Okay. Now coming to design of sewers. Next topic of discussion is design of sewers. Before that, I would like to just discuss a small note point. And that note point is, we have two situations. In first situation, this is my manhole. This is my manhole like this, okay? And in this manhole, at one end, I have this small sewer connected to bigger sewer like this. This is the first situation, okay? I have the manhole where small sewer is connected to bigger sewer like this. This is small sewer and this is bigger sewer. In the second situation, again I have a manhole but this time connection is made like this. This is my small sewer. This is the small sewer. This is the hydraulic gradient line of small sewer. And it is matched with the hydraulic gradient line of the bigger sewer like this. This is the bigger sewer. Now you have two arrangement. This is my arrangement 1 and this is my arrangement 2. Which arrangement I will practically provide while working in the field? So observe this very carefully. In arrangement 1, if any blockage happens in the bigger sewer like this, right? So the waste water will flow back and it will enter in this small sewer. So in first situation, in case of blockage of bigger sewer, there is a possibility of backflow in the small sewer. There is a possibility of backflow in the small sewer. But when we talk about this situation, even in the case of blockage of bigger sewer, the waste water will come back and it will stay here, right? It will not going to backflow in this small sewer. So in first case, since there is a possibility of backflow in small sewer, therefore this is not provided. This is not provided. But in this case, even if the blockage of bigger sewer happens, this waste water will come and rest in the manhole. There is certain less probability of this waste water to go into this small sewer. Or you can understand it like this, the factor of safety for backflow in this condition is more. That's why we provide this arrangement where the hydraulic gradient line of small sewer is matched with the hydraulic gradient line of the bigger sewer. So this kind of arrangement we are providing for connecting small sewer with bigger sewer, right? The hydraulic gradient line of small sewer is matched with the hydraulic gradient line of bigger sewer. So again, this can be framed as a statement in multiple select questions. So you keep a check on this note point. Okay. After this, give the next heading, design of sewers. Okay. So first of all, I would like to tell you, if this is my size of the sewer, if this is my sewer, right, of size capital D, I will never design this sewer to run at full depth. Means I do not want that in the entire depth of the sewer like this, the wastewater should flow. This is not the way of designing the sewer. First of all, what is the first point? I do not want that the entire depth should be used for passing the wastewater. Now I'll tell you the reason. First reason is, when the wastewater is flowing inside the sewer, there is high deficiency of oxygen, due to which the organic matter present in this wastewater will undergo anaerobic decomposition. And anaerobic decomposition leads to the production of gases. These gases include methane, H2S, CO2. Like that, you have a lot of gases produced due to anaerobic decomposition. Especially if I talk about methane, methane is a highly flammable gas. And if methane does not get the area or does not get a volume for its passage, it has a high chance of catching fire, right? So for the accommodation of these anaerobic gases, we will leave some space at the top of the sewer so that these anaerobic gases can accumulate and flow easily inside the sewer. So sewers are never designed to run at full depth. Okay. There is some space left at the top of the sewer so that all the anaerobic gases can accumulate and flow easily along with the water. That space is known as freeboard. So first point is, sewers are never designed to run at full depth. Okay. This kind of design we will not do. Which kind of design we will do? This is my sewer. The size of the sewer is capital D. This will be the surface of wastewater, right? And above this surface, we will leave some area, and this area will be, or this space will be, for the accumulation of all the anaerobic gases, so that these anaerobic gases can flow along the wastewater and may not cause congestion while this wastewater is flowing inside the sewer. Okay. So this is the depth of flow inside the sewer. This small d is termed as depth of flow. So I will write here, small d is depth of flow, and capital D is size of sewer. Small d is the depth of flow. Depth of flow means up till what height the wastewater is flowing inside the sewer, and capital D is the size of the sewer. Okay. So first of all the sewers are never designed to run at full depth. They are designed to run at partial depth, which is small d. Okay. And this space is left for the accumulation of anaerobic gases, and this space is termed as freeboard. This is for accumulation of anaerobic gases. This is for the accumulation of anaerobic gases, and this is how these sievers are designed. Okay, now we'll start with this. If the size of the siever, is less than 400 mm, understand this, if size of the siever is less than 400 mm, then these sievers are designed to run half full. Means your depth of flow will be equal to half of size of the siever. Means if your size of the siever is less than 400 mm, for example, this is your siever of size less than 400 mm, then this will be your depth of flow. They are designed to run half full. This is your depth of flow, small d, and capital D is your size of the siever, right? So if size of the siever is less than 400 mm, they are designed to run half full. So depth of flow is 1/2 times of D. Next, if your size of the siever is between 400 to 900 mm, these sievers are designed to run 2/3 full. These sievers are designed to run 2/3 full. And what do we mean by 2/3 full? If this is the size of the siever, right? This is the size of the siever in the range of 400 mm to 900 mm. They are designed to run 2/3 full. So now this is my depth of flow. This is my depth of flow. This is my depth of flow. So when the size of the siever is between 400 to 900 mm, they are designed to run 2/3 full, right? Next, if the size of the siever is more than 900 mm, then they are designed to run 3/4 full. They are designed to run 3/4 full. Means if this is my size of the siever, okay, this is my center point, then they are designed to run 3/4 full. It means that this is the depth of flow. This is my depth of flow. You can clearly relate from this. This is my depth of flow. That yellow part you can clearly see from this level till the bottommost level of the siever. So this is my depth of flow. And this depth of flow is equal to 3/4 times of D. Here in this case, the depth of flow is 2/3 of D. And in this case, first one, if the size of the siever is less than 400 mm, the sievers are designed to run at half full. Okay. So from this, you can clearly relate that the maximum allowable depth of flow is 3/4 of D and minimum allowable depth of flow is half of D. So whenever we are designing sievers, the depth of flow is always between 3/4 times of D to, so this is my siever, right? This is my siever. This is my siever. The size of the siever is capital D. This is the size of the siever. Now for this siever, the minimum allowable depth is this. And this is equal to this depth of flow is half of D. And this is known as minimum allowable depth of flow. Minimum allowable depth of flow. Means whenever you are designing any sewer, the first thing is the minimum depth of flow should be D by 2, capital D by 2, right? And the maximum allowable depth of flow is 3/4 times of D. This is maximum allowable depth of flow. And this is equal to, this one is equal to 3/4 of D. Okay, so you can clearly see whenever you are designing sewer, your depth of flow should vary between D by 2 to 3/4 times of D. This is the range where depth of flow should be maintained inside the sewer. So this is your minimum allowable depth of flow and this is the maximum allowable depth of flow. Depth of flow will change with respect to the size of the sewer. Okay. Now this is something related to depth of flow. Moving ahead, I need to tell you one simple thing. Whenever you are seeing these sewers, the wastewater inside these sewers flow under the action of gravity, right? We are not using any pumps to suck this wastewater or to transport this wastewater. All the flow which is happening inside this sewer is happening under the action of gravity. If the flow happens under the action of gravity, it is termed as open channel flow. So the flow inside the sewer is an open channel flow. So whenever flow is taking place inside the sewer, it's an open channel flow. Flow inside the sewer is open channel flow. Means under the action of gravity. Flow inside the sewer is an open channel flow that is under the action of gravity. Now observe this very carefully how we design the sewers. So next is design of sewers. So point number 1. Sewers are designed to carry maximum hourly discharge. So what is the first point? First point is sewers are designed to carry maximum hourly discharge. Okay, means corresponding to maximum hourly discharge, you will calculate size of the sewer, you will calculate depth of flow inside the sewer. So first thing is corresponding to maximum hourly discharge, you will calculate size of the sewer. So this is the size of the sewer, capital D. This is the size of the sewer, capital D, and this capital D, size of the sieve, is calculated corresponding to maximum hourly discharge, right? Also corresponding to this maximum hourly discharge, you will calculate the depth of flow inside the sieve. This is my depth of flow. This is the depth of flow inside the sieve, and this depth of flow is corresponding to maximum hourly discharge. I am writing here, this depth of flow is corresponding to maximum hourly discharge. Okay. So using maximum hourly discharge, we calculate size of the sieve and we calculate depth of flow of the sieve. This is the first point. Now second point is, sievers are checked for the development of self-cleansing velocity corresponding to minimum hourly discharge. Minimum hourly discharge. Two things, self-cleansing velocity and minimum hourly discharge, right? So this is the depth of flow corresponding to maximum hourly discharge. Now the same sieve is checked for the development of self-cleansing velocity corresponding to minimum hourly discharge. Now you will say, sir, what is this minimum hourly discharge and what is the self-cleansing velocity? So this is your depth of flow corresponding to minimum hourly discharge, right? This is your depth of flow corresponding to minimum hourly discharge. Corresponding to this depth of flow, there will be one flow velocity like this, right? There will be one flow velocity like this. Now this flow velocity at minimum hourly discharge, I am right here, I'll write here, minimum hourly discharge. The flow velocity corresponding to minimum hourly discharge should be equal to or greater than the self-cleansing velocity. The velocity of flow corresponding to minimum hourly discharge, velocity of flow corresponding to minimum hourly discharge, minimum hourly discharge. This should be greater than or equal to the self-cleansing velocity, VSC. Now what is this self-cleansing velocity? My dear students, self-cleansing velocity is that velocity which will not allow the solids to settle while this wastewater is flowing inside the sieve. Okay. Self-cleansing velocity is that velocity that will not allow the solids to settle inside the sieve when this wastewater is flowing inside the sieve. The turbulence corresponding to this self-cleansing velocity is so much that it will not allow these solids to settle inside the sieves, right? So we do not want these solids to settle inside the sieve. Reason is, if these solids settle inside the sieve, it will lead to the incrustation in these sieves. Means all these solids will settle at the bottom of the sieve, which reduces the discharge carrying capacity of the sieve. That's why we do not want these solids to settle at the bottom of the sieve. Okay. So self-cleansing velocity, you understood what is self-cleansing velocity? Self-cleansing velocity is that velocity corresponding to which these solids will not settle at the bottom of the sieves. Also, if your velocity is equal to the self-cleansing velocity, then whatever solids by any other reason, if they have settled, those solids will even come back to the wastewater. It is also acting as a scouring velocity, right? Scouring means whatever solids are there at the bottom, they will also come back to the wastewater. Self-cleansing velocity will create such kind of turbulence that will not allow these solids to settle inside the sieve. Okay. So while designing the sieve, 2 points you need to keep a check. First point is, sievers are designed to carry maximum hourly discharge. For maximum hourly discharge, you will calculate size of the sieve, capital D, and you will calculate depth of flow, small d, corresponding to maximum hourly discharge, right? There is no problem of solid settling during maximum hourly discharge. Problem starts when your discharge reduces. So during minimum hourly discharge, the velocity of flow inside the sieve should be greater than or equal to the self-cleansing velocity. This self-cleansing velocity will not allow the solids to settle inside the bottom of the sieve. Even if some solids are settled due to some other reason, it will take back these solids back to the wastewater. So these two things you should keep a check while designing the sievers. So this is how your sieve design is done, right? This is how your sieve design is done. Now there is one expression for this self-cleansing velocity. So self-cleansing velocity VSC is equal to under root 8K by F GD into G minus 1. This is your expression for self-cleansing velocity, where K is a constant depends on type of suspended solids. Depends on type of solid. F is the friction factor. This small d is not the depth of flow. This small d is the size of the solids. And capital G is the specific gravity of these solids. Capital G is the specific gravity of solids, right? So this is how you do or design your sievers, right? Chala. So this is the thing, this is how you design the sievers. These are some of the basics that may help you to understand the topic in a better way, right? So this is all for the day. Thank you so much for listening patiently. I'll see you in another session, and I'll be coming up with the most important topic of environmental engineering, that is your trickling filter. So thank you so much for listening patiently. Have a very good night ahead. Thank you so much. Hello sir, happy Teachers Day. Thank you so much Nikhil. I'm good. Okay Nikhil, have a great night ahead. Thank you so much.